Okay. So we started to talk the last time, and we're going to continue this with parallel series circuits. So it's not series parallel, but this will be parallel series. And what I mean by that, I'm going to show you a circuit. And let's go ahead and do this guy, this guy, this guy, this guy. We'll have a voltage source. Come up here and come over here. Create a resistor. Create another resistor. Come down here. Create a node. Call that node B. The one at the top, call that node A. And then over here, resistor, 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 another resistor, 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 down to here. And we will call this a 27-volt source. We will call this R1, R2, R3, and R4. Oh, somebody's clicking on. Let's see who else is here. Let's try this. Mr. Cortez, welcome. We can see you. We can see you in 2 different places. If you've been waiting long, I apologize, but we only need to see you in 1. And here, 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 here. Enter full screen, speaker view, and there. Okay, is this a little better? Or was there any change?
Looks good.
Okay, so what we're going to do is to show you how we go to analyze this circuit once I put in some resistor values for all of the considerations that we're going to be interested in. And so the considerations we're going to be interested in will be for R1, R2, R3, R4 totals. And we would be interested in the following information. Voltages for sure. Current is for sure. And resistance as well. So there's our VIR chart. Now, the resistor values that I'm going to have you think about for this particular analysis will be as follows. Let's go ahead and put R1 up here will be 780 ohms. So that's 780 ohm over here. I will have R2 be 1.5 K ohms. So I will have 1.5 K ohms over here. R3 will be 560 ohms. I will have 560 ohms over here. And then R4 will be, let's say, 330 ohms. This will be 330 ohms. My voltage source is given as 27 volts, so I will write my 27 volts right there. So that's the information we're going to start with. Why don't you get that drawn, written down, and I'll catch up with Mr. Cortez. So Mr. Cortez, welcome to our discussion. I see you logged in 3 places. Only need to hear your voice in one of them. How are you doing, sir? Christian, can you acknowledge, say hello? I see you as part of our group, but I don't hear you. Let me check the, you can also type in chat if your microphone and camera are not working, but I see 3 separate logins for you, but I don't hear any response. So I'll keep trying. There may be some technical issues on your end. Hopefully you can hear us. All right. So how do we go about working this particular guy out? Working this particular guy out will be done this way. The process, there's a process. Let me find the right pen here. All right. Process. The process is called circuit reduction. That's the name of the process. How is done by redraw circuit. The why, to simplify. Okay. So the process of analyzing what we have here can be described simply as circuit reduction. The how that we're going to implement is by redrawing the circuit. And why are we doing this is to simplify, because right now we happen to have 4 resistors. We have to simplify this to something a little more understandable. And so my recommendation is, since I have this drawn here, I'm going to redraw this. I can redraw it to the left, right, doesn't matter. Some of us find it very convenient to draw it directly underneath the original circuit. So I will create my node A. Here's my wire coming out here. Here's my voltage source. And this will come down here. Here will be my node B. And this will come over to here. This will come down. This will come over to here. This will come up like so. But what's interesting is, instead of these 2 resistors being separate, you can see that R1 and R2 have what electrical relationship? Are they in parallel or are they in series with each other, R1 and 2? Rebecca, what do you think? Microphone.
They're in series. Sorry.
They're in series. And we define that they're in series because there is only one current path between R1 and 2. So because they are in series, could I combine these 2 into a single resistance? And I will do so. These will become one single resistance that we will label as REQ1. And what EQ stands for, EQ stands for equivalent. Meaning that this single resistor represents the sum of these 2 guys. So if you go to add these guys up very quickly, you're going to have 780 plus 1,500, yes? So 780 plus 1,500 gives you some kind of a total. You need to do that on your calculators. And 780 plus 1,500, the fastest way to add. So Pauline, what do you have?
I get 2.28 kilo ohms.
Excellent. 2.28 kilo ohms. So does everybody see how we handled the first branch, which had 2 series resistors that became a single equivalent resistance? We name it as REQ number 1, because over here in a moment later, we will have an REQ EQ number 2. So there, the subscript number 1 and number 2 differentiates first branch equivalent resistance from the second branch equivalent resistance. So now I'm looking for a total for R3 and 4. R3 and 4, as you can see, is a single current path, which puts R3 and 4 in series with each other. Therefore, if I wanted to combine them into a single equivalent resistance, I simply add these two numbers. And when I add these two numbers, Gabe, what value does R3 and R4 add up to be? Unmute your microphone and give us your answer.
890.
800. How many people agree with 890? Raise your hands. Yes. This is good. 890 ohms. And we would write that down. So far, so good. Now, our voltage source still hasn't changed. It's still 27 volts. So in this very first step of the process, what is the process called again? It's called circuit reduction. How are we implementing the process? We are by redrawing the circuit. And the purpose of doing so, the why, is for what purpose? To simplify. Have we simplified the 4 resistors now down to a 2 resistor circuit? Yes. Then what do you think the next step is going to be? We're going to redraw again. Here, here is my point A. Back over here. Here is my point B. And I will have these two guys combined. So what is the relationship now between REQ1 and RE2 as I've drawn in this middle circuit? Question goes to Andrew. What is their relationship to each other? Are they in series? Are they in parallel?
They're in parallel.
They're in parallel. So what I'm looking for is these two resistances, the equivalent resistances, coming up to be some kind of a total here. So what would be one method that you could use to calculate these guys in total?
You could use the reciprocal theory.
You can always rely on reciprocal. Reciprocal will never let you down. You also can remember that because these are two values, you could also use product over sum. So you could take 2280 plus 890, divide by 2280, 2280 times 890 over 2280 plus 890. So you can do product over sum, but there's no other shortcut that we can use. So I would recommend, let's go ahead and stay with reciprocal method. Now, I would like each of you to do a calculation, but actually before you even touch a calculator, can you guesstimate, can you have a gut impression of what those ohms ought to be? Are they going to be higher than this? Are they going to be lower than this? What do you think? Pedro, what do you think? What do you think my total between these two values is going to end up being?
Lower?
Lower than what?
Than the overall resistance?
Well, we're looking for the overall resistance, but you almost have the right words. What I was hoping to hear you say, and let's see, Kyle, what do you guesstimate the? And I'm not looking for a number. I'm just looking for a concept.
I think it's going to be lower than the. I think it's going to be lower than the REQ1.
For sure, it's going to be lower than REQ1. I'm looking for something else. Yes, Rebecca, you have your hand raised.
Shouldn't it be lower than REQ2? Because shouldn't the total be lower than the lowest ohmic branch on a parallel circuit?
Precisely. That's the verbiage that I'm hoping each of you have emblazoned to the back of your retinas, okay? That the total resistance of any bank of resistors, remember the nickname for parallel circuits is they're called banks. This is one branch, this is a separate branch. And the total for these guys must always be less than the lowest ohmic branch. So it's got to be less than the 890. That's the verbiage that I want for you to instill in your hearts, to be able to just, okay, boom, I don't know anything about the actual number, but I do know it's got to be less than 890. So if you calculate something more than 890, boom, there's something wrong in your calculations. So now that you've had some time to do these calculations, I'm now going to call out for an actual number here. So I'm going to do reciprocal plus. Okay, I'm looking for the very first digit of your R total. Christian, are you with us?
Yes.
Hey, there you are, Christian. Fantastic. Have you been following this along with us?
I just joined like 10 minutes ago because it wouldn't let me join earlier. I don't know why.
Yeah, sorry. We need to start closer to the beginning of the hour. And so once I start talking, I apologize. I may not see somebody in the wait, and so part of the delay was waiting for me to notice that you were in the wait room. So as a recommendation for all of us, my friends, is really try to start right on the hour, and that way I can go through the login. So anyway, I'm glad you're with us. We're working on this particular exercise. This is being recorded, and so you'll be able to see the recording later on, but nothing like participating with us. So I'm glad you're here with us. Let me continue. So Wenbin Lao, do you have a total resistance number that you are happy with?
No.
No? Okay, keep working on that. Pedro, do you have a total? Okay, don't shout out the answer, but Pedro, give me the first digit of your answer. First digit only.
6.
Good. All right, that's good for now. And how about Gabriel? Do you have a total you're happy with?
2.
No, the second digit is not going to be a 2, and neither is the first digit. So I'll show you how to work that out. Pauline, do you have the second digit for us?
Second digit is number 4.
The second digit is a 4. Very good. So the first digit is a 6, and then we have a 4. I'm looking for the third digit. Rebecca, do you have the third digit for us?
0.
0 is correct. Excellent. Now I'm looking for the digit after the decimal point. Kyle, do you have that?
No, I do not. I'm still doing the calculations. I got it wrong the first time.
Andrew?
Yeah, I got it wrong too. I'm working it out right now.
Okay.
Where I messed up.
So let me show you what you need to do in order for us to achieve the desired result. We have these two guys in parallel with each other. So as a reminder, the keystroke sequence, let's do this with decimals first, just to keep it simple. This is 2,280, yes? And you have to hit this reciprocal key, which is an X -1. In some calculators, it might be a 1/X key, but somehow you need to engage. This is called the reciprocal key. You need to engage this function, and it may be a second function on your calculator. So you might have to hit second and boom, one of these. But however it's done on each of your calculators, you take the first number, you reciprocate it, and then you do an add. Then you take the second number, and you also reciprocate it,
Tonight?
and then you hit equals. Then you hit the reciprocal one more time, and then you hit equals. So that is your keystroke sequence to successfully calculating this number plus all the digits after. So do that now.
Oh, okay. I see where I messed up now.
Okay.
I got a number after the decimal.
Okay, what's your first digit after the decimal point, Kyle?
I got a 1.
1 is very good. Okay, so that is correct up to this point. And Wenbin Lao, do you have the next digit after the decimal point? Mr. Lau? You need to unmute your microphone. Gabe Orozco, do you have that number? You need to unmute your microphone if you're responding. Andrew?
I got it. It's going to be a 3.
It's going to be a 3. And that would be correct. And this would be followed by the omega symbol, yes? So the important thing to recognize here on your calculators, you should end up with a 640.126183, something. It keeps on going. But what you're going to need to keep in mind is properly rounding off. Now, our standard is we're going to be rounding off to the second digit after the decimal point. You always need to look at the third digit for guidance. And the rule of thumb was, if that third digit is 5 or more, then what you need to do is round up your second digit. And that's why the 640.12618 becomes a 640.13 on your answer sheet. Everybody clear on that? Okay? Okay, cool. So now we can fill this guy in over here as 640.13 ohms. Yay. Terrific.
I'm getting a different answer for that reminder you put up there. Yeah, I keep getting a 35.88.
You're typing in 2,280 reciprocal plus 890 reciprocal equals, and then you hit reciprocal, and then you hit equals.
Yeah.
And what does your calculator show you?
35.88.
And who is this?
Gabriel.
Gabriel. Okay. Gabriel, where's your, oh, there you are. All right. So Gabriel, show me your calculator. All right. So why is it answer squared? Why is it answer squared? Squared is not the function we use. I see an answer squared. There's no square in this whatsoever. This is an x negative 1 or a 1 over x function on your calculator. So yeah, you're going to need to...
Oh, I see what I was doing. I wasn't using the second F. I was just clicking the x negative 1.
Okay, so as I verbally pointed out on my screen, yeah, as I verbally pointed out, however you get to that reciprocal function, some of you may need to hit second and then this function. It just depends on your particular calculator. I'm not going to write out seconds. I'm not going to write out this 1 over x. I'm just going to use the standard x negative 1. But that's the process you need to learn on your own calculator, how you get here, okay? So once you do the recalculation, can you go ahead and show me on your calculator your final result? And the answer is 640. Okay, perfecto. I see the reciprocal sign, answer 1. Excellent. Feeling better, Gabe? I'm feeling better. But you're feeling better. That's great. All right, my friends. Now, back to my screen. All right. We have 3 columns, 5 rows, that's 15 cells, and this is all we filled in so far. We've got to knock out the rest of these. So how do we go about doing this? What should we do next? Somebody raise their hands. Let me know what's going on. Yes, Rebecca.
We can solve for I total.
This guy right here?
Yeah.
And so this I total represents our most recent circuit, I think. We happen to have in our most recent redraw, the voltage source hasn't changed. It's still 27 volts. point A is still on top, point B is still on the bottom. We've completed our process, circuit redone, we've redrawn to simplify. We've got 4 resistors down to 2, down to 1. It don't come any simpler than a single resistor, R total. So Rebecca says we can just use Ohm's law to take the 27 volts and do something with it with the RT in order to calculate the current. And so as a gentle reminder for everybody, since it's been a little bit of time since we last chatted, there's your Ohm's law circle. And so if I am looking for I, what do? I cover the I. I would be equal to, what's left over is V over R, yes? So could we go ahead and everybody do that now? Take the 27, divide by the 640.13 or whatever your calculator has. I'm going to use all of it. So 27 divide by up here, boom, and enter. And so your suggestion is spot on, Rebecca. That's excellent. And the first digit of the answer, Rebecca, what do you have?
4.
Is a 4. 4 is a good number. We will write that down. Pauline, do you have the second digit?
Second digit is 2.
Second digit is a 2. That would be correct. Third digit, calling out to Gabriel. Do you have that third digit? The decimal, the digit after the decimal point.
I was going to say because it's decimal. And then 1.
Okay, would be a 1. That would be correct. And then the second digit after the decimal point, Christian, do you have that for us?
I rounded it up to an 8.
You rounded it up to an 8. That would be correct. And my units on this Pedro would be what?
Milli.
Milli is correct. And my electrical quantity would be what, Andrew? Milli what, Andrew, is the question.
Amps.
Milliamps with an A, like Andrew, huh? How about that?
Yeah.
Hey, all right. Everybody in agreement? We have 42.18 milliamps, yes? And what your calculator should show you is all these giblets after the 0.7. So it's a 0.179.17918, blah, blah, blah. You look at that third digit, it's more than 5, which means you have to round that 7 to become a 0.18. Is everybody clear on that process? Cool. This is great. All right. Now that we have our master current, could I write that information here so that I can see it? Remember, this is positive on this side. This is negative on this side. And the current flowing in this current circuit right now is 42.18 milliamps. Yay. That's our I total. So we'll just go ahead and write that in. So have we thoroughly analyzed this third circuit for total ohms, total volts, and total current? There's nothing else for us to do in this particular guy. Everybody happy with that? All right, so now we are looking at 8 more squares to fill in, 8 more cells. What do we do with this? Who's got an idea? Where do we start?
Well, isn't the voltage the same in all of these? Was there parallel?
Who said that? Gabriel?
Christian.
Christian, yeah, Christian, yeah, you're right, absolutely. So if we take this 27 volts, the voltage is the same because this is a parallel circuit. So what do I do with that 27 volts? How's that help me fill in anything over here?
Divided individually by the resistances.
Divided individually by the resistances. Okay, so we can do voltage divider as one method of filling in some of these. That would be a good suggestion. Does anybody else have we can do this several different ways. I'm just trying to see how many people have how many different kinds of ideas. So dividing that 27 volts into the resistances to find individual voltages would be one method. What would be another method to fill in some of these numbers? If we have found one current, have we found all the currents?
Yes.
If we found this current, do we take this current and fill this in?
Yes.
Yes.
That would be a no, my friends. And I'll tell you why. you would fill this in only if this was a series circuit. As you can see, the original circuit is not a series circuit. So because you find I total, you have found I total, and let's go to the middle circuit so you can see this a little better. I total flows from the source, and it is indeed at this point 42.18 milliamps. It flows to this node B. When it flows to node B, do you see that the current will split at node B and go up two different paths? So this 41.18 can't be the current that flows up through here, and it can't also be the current that flows up here because it splits. Part of the current, part of that 42.18 flows up in this branch, and part of it flows up through this branch. So if you can understand that this 42.18 milliamps that flows out of the source to node B splits, it cannot be filled in on all of these cells. What else can we do? That was a leading question. That was, I didn't mean to cause anybody to fall into a trap or anything, but that's what we call a leading question. When you're at a job interview and the job interviewer asks you the very same question and nods his or her head, oh yeah, we found this current, now we can fill this in, right? And the person is nodding their head up and down, and I'll show you what I mean. So here we are. You found the total current. Because you found the total current, we fill in all the currents, don't we? Yes, yes, yes. And you're supposed to say no, 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 because you know better. Okay. So that being said, because you know better, what would be another way for us to do this? We have one suggestion that was valid. Voltage divider is one method to split this up and find the voltages. What else can we do? Another idea, because there's several different ways we can do this.
You divide voltage with resistance.
Who said what?
You divide.
No, who?
Gabriel.
Gabriel. Okay, so Gabriel, what are you suggesting?
You get your voltage and you divide it by your 780 amps, and you just keep going down.
We don't have 780 amps.
I mean, ohms.
Ah, okay. We take this 27 and divide by 780.
Yes, correct.
Ohm's law.
I think all the voltages are the same.
Yeah, Ohm's law won't allow us. Ohm's law won't allow us to do that because that 27 volts is not solely across 780 ohms. That 27 volts is across two resistors. So we cannot take that 27 and divide this by here, because that 27 is, as Christian suggested, part of that 27 is across R1, another part of the 27 is across R2. So we can't take 27 divide by 780. So that aspect won't work because we don't have 27 only across the 780. You keep thinking, the more we think, the more we verbalize, the more we throw out there, the more we can discover what we can cast aside, and ultimately we'll get a method. Another
But
method somebody would like to
second
suggest?
picture though, right? On the RQ.
Oh, hold on, I got Bolito coming in. Hold on. Where's Bolito? Bolito. He needs the meeting ID. Great. I sent out 2 emails. Oh dear. Hold on, my friends, just one moment. I don't want to leave anybody behind. Oh Lord. I think the easiest thing to do is probably, no, not here. Not here. Let's go here. And here. And not here. Not here. Where did he come in on? He came in on Canvas. Okay. So on Canvas, Would you please check email? Enter and send. Okay, hopefully he will read his email and click the link that you all did and be able to join us. All right, getting back to some suggestions. Pauline, you have an idea?
Well, I was just reading the summary, series parallel.
Summary is a good place to be, yes.
So
What did you cover from the summary?
if IR1 equals IR2 equals IR3 on the series.
Correct. In series, the current that flows through R1 will be the same current that flows through R2. So
Correct.
that current through here will be the same.
Correct.
What can we do to find it?
So do a current divider.
Yes, we could use that as an alternative. So this, as I mentioned, there's several different ways we can do this. So let's take a look at methods. Methods of analysis. Methods of analysis after I-total. And so one of the methods suggested, there's Rolando. Cool, hold on, let me click on this. Come on, mouse, here. Come on, Rolando. And admit, there he is. All right, Rolando, thank you very much for joining the meeting. You can unmute your microphone and say hi to everybody real quick. And he's getting set up. But here, let's go ahead and reiterate what some of your classmates have suggested. So Christian has suggested VDF, voltage divider formula, to find VR1, VR2, etc. Okay, so use that. Number two, we can use CDF, current divider formula, to find branch currents. We can certainly do that. So those are two methods already. Voltage divider formula, current divider formula. We've talked about before. I won't take the time to review here because I want to give you the fastest, smartest, not hardest way to resolve this. So where we are, once we find the 40.18 milliamps that flows out of here, we can use current divider and do that, because current divider formula, if you remember, your IRX was equal to RT over RX times IT. A little bit of calculation to do that, but I have a simpler method for you. The simpler method is to use Ohm's law. Ohm's law. And what you want to remember about Ohm's law is that your Vs is equal to V1 equal to V2 in parallel. So your I1, not IR1, but I1, meaning the first branch current, is going to be equal to V1 over REQ1. Very simply, look at this circuit here. You can copy that down later, or again, review the notes and get that later. But look at the circuit here. Don't I have a simple parallel circuit? And you know from your notes, in a simple parallel circuit, isn't voltage, that 27 volts, the same across the first branch and across the second branch? We're not going to use that in the first circuit because I've got two separate series resistors, but don't I have a single resistor in this middle circuit in this branch, and don't I have a single resistor here? So if I wanted to find the branch current, couldn't I just simply use Ohm's law and multiply my 27 volts, divide my 27 volts by 2.28 k ohms? Ohm's law. This divide by these ohms, won't that give me my current in this branch? Yes, it would. And that's what I mean here. I1, not IR1, but is I1, meaning the first branch current is equal to the branch voltage divided by REQ1. So everybody with your calculators, take 27 volts and divide by 2,280. And you end up with a current. And that current shall be called I1. And I1 will be equal to the following. So I'm going to be calling out for the first digit. And Rebecca, do you have that first digit for me?
1.
First digit is a 1. And I'm looking for a second digit. Let's see, Pedro, do you have that second digit?
1.
Is also a 1. Very good. Now I'm looking for the digit after the decimal point. So the first digit after the decimal point, Christian, what do you have?
8.
8 would be correct. And now I'm looking for the second digit after the decimal point. Mr. Lau, do you have that? Would be a 4. That's correct. And that's milliamps. So are we in agreement? 27 divided by 2,280 gives us 11.84 milliamps that flows up through this branch. Yes? By the same token, we can calculate the current on this branch because we know that 27 volts here is also across 890 because this is a parallel circuit. So now can we take the 27 volts and divide by 890 and calculate the branch called I2? So I2 would be 27 and divide by 890. And I'm looking for the very first digit of this calculated current. Pauline, do you have that first digit?
First digit is number 3.
Okay. Rolando, how are you doing? Do you have this this calculation for us? 27 divided by 890.
Yeah, it's 3.
Okay, first digit is a 3. Very good. Now I'm going to call out for the second digit. Gabriel, do you have that second digit? Unmute your mic, pal. Kyle, do you have the second digit?
0.
0 is correct. Now I'm looking for the digit after the decimal point. Rebecca, do you have the digit after the decimal point, first one?
3.
3 is correct. Now I'm looking for the second digit after the decimal point. Gabriel, are you with us? Do you have that second digit after the decimal point?
No, I'm still doing the math, sorry.
Well, it's 27 divided by 890. Those two numbers, okay? Everybody should have this. Christian?
3.
No.
4.
Okay. It would be a 4 is how we should round it up. And what are my units here, my friends?
Milliamps.
Milliamps. Okay, cool. So look at the second, this middle circuit. This 2.18 milliamps splits at node B to become 11.84 current going up, and it splits to become 30.34 going up here. What happens at the top of the circuit? At the top of the circuit, doesn't this current wrap around, come to node A, and isn't this 30.34 milliamps here? And isn't it adding with 11.84 milliamps here? Won't these two combine to give me my circuit current of 42.18 milliamps? Is that right? Do those numbers add?
Yeah.
How about that?
Yes.
So what the current that goes into a bank has to equal the current that comes out of the bank. Are we clear on that? I will write this down. Current entering a bank must equal current leaving that bank. And bank, if you remember, was a nickname that was given for a parallel circuit. So the current, the bank is comprised of these two equivalent resistances. 42.18 milliamps is flowing in. It splits apart into these two branches to become 11.84 and 30.34 milliamps. At the top of the circuit, they combine and they do add back to the original amount of current going back to the source. Isn't this a marvelous thing? And with this analysis, can we now bring some of this information back to the original? We started in our analysis with this, simplified to here, simplified to a single resistance. From here, we found our RT. Here we found our IT. We bring this IT information into the middle circuit. The IT we discovered split. Now we can take this information back up to the original circuit. And what information do you think we're going to take up here will be this. We now know the current that flows up here, and we now know the current that flows over here. The current that flows up here through between A and B in this middle of the circuit is my 11.84 milliamps, and the current that flows on the outside is my 34 milliamps, sorry, 30.34 milliamps. What's that tell you about what we can fill in here? Do I now know the current through R1? Yes. Do I now know with confidence the current through R2? Yes, because the current is the same in a series circuit. Over here on this branch, I have a different current, but I have two resistors in series, and because I have two resistors in series, isn't that 30.34 milliamps flowing through R3 as well as R4? Can I fill that information in my VIR chart? Yes. Yeah. So I will write 11.84 milliamps here, 11.84 milliamps here, and 30.34 milliamps here, and 30.34 milliamps here. There we go. The current column is now complete. What else is left to do is to finish calculating our voltages, yeah? And to calculate our voltages, wouldn't we employ a simple method of Ohm's law? Again, if I want V in my Ohm's law, don't I cover up the V with my finger? And that's equal to what's left over, I times R, yes? So I'm going to do the same thing here. If I want V, my V is equal to my I times my R. Do I have an I? Do I have an R in each of these rows? So I can do these calculations. So everybody go ahead and do these calculations right now. I'm going to call out names for answers in a moment. Oops. One, two, four, and then here times. Okay, and here, 0.6, and then here times this guy. I have 3.9, and then I have this guy times I have this guy here, 0.01. Cool. All right. Okay, first one. Let's take a look here. Okay. By raise of hand, who would like to offer the first one? Rebecca, go ahead and give us what you calculate for the first one.
9.24 volts.
9.24 volts is correct. Thank you. Who would like to volunteer the second one? Raise your hand. me get to a different screen. Come on, mouse. I can't see everybody. Mouse. Got too much stuff on my desk. I'm sorry. If you're raising your hands, I'm sorry. I can't quite see everybody yet. Okay. All right. So somebody raised their hands for VR2. Remember, it's only this current times this ohms. This
It's
current times this ohms. Pauline, yeah, what do you have?
17.76 volts.
That's the year our nation came into being, the year 1776. How about that?
Yeah,
You are correct.
absolutely right.
That is correct. Now, all right, who would like to raise their hands and give me VR3?
It's 1699.
1699, Gabriel, is correct. Thank you. And who would like to give me the answer for VR4?
$10.01 volts.
10.01 volts is correct. And let's see if those numbers make sense in our original circuit here. All right, so I will speaker view, and I'm actually going to write this information in on our schematic. So I have 9.24 volts here, and I have 17.76 volts here. Take a look at that first branch, if you would, my friends. I wrote 9.24 volts across this first resistor, 17.76 volts across the second resistor. Should these two voltages add this branch to give us the 27 volts that's over here?
Yes.
They do. Just like the resistors in series add, their voltage drops in series also add. So the 9.24 plus the 17.76 add exactly to 27 volts. Let's see if the same thing happens on the other side. On the other side, we had 16.99 volts. And then on the this resistor, we had 10.01 volts. And guess what? Doesn't the 16.99 add with the 10.01 add up to be the 27 volts that we started with on over here? Isn't that exciting? Cool. Guess what you're going to see for homework? More of this type of analysis, okay? And you'll be able to review all of our steps in glorious detail if they can give me my recording back in a timely fashion. It's going to be a huge upload, so it might not happen that you get it back this afternoon, but I'll try my best to make it available to you so that you can see what's going on with this. What to ultimately be able to do is to do this in Tina. So speaking of Tina, I am on Zoom, no, I'm on Canvas on my other screen. Let me go to our class 50 during the day. Come on, get there. And it's thinking Canvas is slow. Well, maybe Canvas isn't slow, maybe because I'm also doing Zoom in the background. It's using up a lot of resources. I think that's more the case. And checking on your progress of assignments. It's thinking. All right, while Canvas is thinking, does anybody have any questions regarding this process of parallel series circuits? To analyze parallel series circuits, and why is this called a parallel series circuit and not a series parallel? Here's the reason why. Take a look at the original circuit, and as you look at the original circuit, the current that leaves the source comes down and it sees node B. Between this negative plate, between the negative plate of the voltage source and node B, was there any series component in that wire whatsoever? None. Take a look at the current coming back from node A. From node A, the current coming back is there any single series element in that wire between node A and the positive plate? The answer is no. So what happens with this particular circuit, it does split at node B and the currents combine at node A. It is fundamentally a parallel circuit, as evidenced by the middle drawing. But it has series elements in it. It has series elements in first branch, and series elements in the branch. For this is called a what? A parallel series circuit, in contrast to a series parallel circuit that we had done before. Okay, so that's the reason why we named this the way we do. Are there any questions as to how this is calculated?